So section 1.3, scientific measurements. In science, we make a lot of measurements. And anytime you're measuring something, that is necessarily a quantitative property of matter. It's a property of matter that can be measured and assigned some sort of a number. You can measure the temperature of something, the length, the mass, the volume. Some of the instruments that we use or devices for measuring in science, to measure length, we might use a meter stick. That's just like a yardstick, except it's got centimeters and it's 1 meter long instead of a yard. Or we might use a metric ruler. For measuring liquid volume, we have a variety of different types of glassware. Some of them are pictured here. This is a volumetric flask. That's useful for measuring one single volume. It's got a mark on the neck, and so that one's 25 milliliters. So it's not good for measuring any other volume, but if I need 25 milliliters, I could use that to measure it. This is a graduated cylinder. You can measure different volumes with that. This is a pipette, a 25 milliliter pipette. We would use that to measure out as precisely as we can 25 milliliters of a liquid. And this is a burette, which is also a rather precise piece of glassware and is useful for measuring different amounts of liquid. So those are the types of things we use to measure volumes of liquids in chemistry. To measure the mass of something, we'll generally use a balance, an electronic balance. And measuring temperature is very similar to measuring temperature in everyday life. What do you use? A thermometer. The difference is that scientific thermometers don't have degrees Fahrenheit on them. We use other units. So we make all these measurements. It's important to realize that measurements are useless without a unit. They're meaningless. So if I tell you it's 30 to my house, does that tell you how far away my house is or how long? I mean, you can't even tell. Am I talking about how long it takes me to get here or how far my house is? It could be 30 feet, 30 meters, 30 kilometers, 30 miles. This is more like 30 miles. My house could be 30 years old. It could take me 30 minutes. It just doesn't really tell us anything. You go to McDonald's and say, I want 2. They're like, 2 what? You want a number 2 meal? You want 2 French fries? 2 coffees? What do you want? It doesn't tell us anything. In chemistry class, it's really, really important that the unit be attached to the number. If you're just putting down numbers, they don't mean anything. And this is something I see students do a lot. And they do calculations. We're going to learn how to manipulate units today. And they'll start with the unit and they'll end with the unit, but in between they just got a bunch of numbers. It is crazy easy to make mistakes when you leave off the units. Every time you write a number, you write the unit associated with it. And that's part of what I'm going to be doing when I'm looking at your homework journals to see, are you following through on that? Are you writing the units? Okay? So, what are these units? Well, we are all familiar with the English system, miles and inches and degrees Fahrenheit and quarts and things like that. Scientists don't use the English system of measurement. In fact, most of the world doesn't. Did you know there's only 3 countries that still use traditional units? The United States, Myanmar, do you even know where that is? Formerly Burma, and Liberia. Every other country uses the metric system. What is wrong with us, right? The metric system can be a little intimidating if you're not familiar with it, but I hope to be able to show you and convince you that it's actually a beautiful system. Once you learn how to use it, it is so much easier than the English system. Do you know how many teaspoons are in a cup? I can never remember that. I can remember 3 teaspoons in a tablespoon, can't remember the tablespoons to cups. All these relationships between the English units are weird numbers. 12 inches in a foot, 5,280 feet in a mile. Where do these things come from? Well, they do have historical background. Do you know how they originally defined the foot? It was the length of the king's foot. So then you get a new king with bigger feet. What happens to your system of measurements? It's all messed up, right? And so it just kind of got pieced together over time. And then people said, well, hey, maybe we could come up with a better system. And so they came up with the metric system. And the metric system has gone through a couple iterations, a couple revisions. What we now use is called the International System of Units. It's called the SI system because when you say the name of it in French, the word for system comes first and then international. So that's why it's SI. And I guess that looks better than IS because that might be is. Anyway, the SI system of units is really just a revised metric system. Okay? There are subtle differences between the metric system and the SI system. I don't care about those small differences. In my mind, it's basically all the same. So in the SI system, there are 7 base units, and they're listed here. All of the other units are derived from these base units. And so we're going to use meters, kilograms, seconds. We're not going to run across amperes in this class. We're going to use kelvins and moles, and we're not going to use candles or candelas. Okay, but they're in the metric system. It's important to have units of different sizes because we want to match the size of the unit with the size of the thing we're measuring. I would measure the distance from Fresno City College to my house in Reedley in miles, right? It's roughly 30 miles. It would be silly to measure it in inches, right? Because it would be this ginormous number. It doesn't make sense. I don't want to measure the length of this piece of paper in miles because it would be really, really small. It would be better to use inches, right? Even feet would be kind of iffy. So in the metric system, instead of having a bunch of different units that are related by odd numbers, we use prefixes that have a meaning equal to some power of 10. And so we make the units larger or smaller by multiplying them by factors of 10. So in a way, it's a little bit related to scientific notation. So the size of the units gets changed by using a set of prefixes. The nice thing is this one set of prefixes is used for all the units. So you memorize one set of prefixes and you're set. You don't have to worry about how many tablespoons in a cup. You need to memorize these prefixes. Okay? There are some things that you just flat out have to memorize. There's not really any logic or understanding behind them. It's just because we decided that's what it is. So here are the metric prefixes. There are more, but this is the table in your book, and so this is what I'm going to ask you to memorize. These are the names of the prefixes. These are their symbols, and this is the meaning. Okay, what I want you to memorize is the power of 10 meaning. Okay, it also shows it to you in the decimal form, but I don't think that's all that useful. So what's a good way to memorize these? Index cards. Make yourself some flashcards. Put the symbol on one side, put the meaning on the other side. Okay? You need to memorize these. You're going to need these in Chem 1A. You'll need them in Chem 1B. If you're taking physics, you'll use them in physics. They're just used all over the place. I do want to point out that some of these are capitalized. Tera, giga, and mega make the unit much larger. So 1 teragram is 1 times 10 to the 12 grams. That's a lot. A 1 with 12 zeros after it. Mega, we actually use that term. You hear, oh, that movie star makes mega bucks. Well, what does mega buck really mean? It means $1 million. So a mega buck would be $1 million. So mega is 1 million, and then giga, I don't even know what the name for that is. Would that be? No, I don't know. Anyway, giga is 10 to the 9, tera is 10 to the 12. Really, really big. The capitalization here is important. Here we have capital M, down here we have lowercase m. Lowercase m represents milli. Milli makes it smaller. Milli multiplies it by 1 times 10 to the minus 3. So it makes the unit smaller, whereas mega, capital M, makes it bigger. So that kind of makes sense. The big M makes it bigger, the small m makes it smaller. Then we also have this other prefix that starts with an M, micro. We've now used both of our letter M's in the English alphabet, capital M and lowercase m. So then we go to the Greek alphabet, and this is the lowercase Greek m, and it's called mu. So mu stands for micro. And when you write mu, this is always interesting. You see students, they just really struggle with how to write this. Okay, it looks a little bit like a U, but it's got a tail at the front. So just start at the bottom and come up and make a U. And that'll be a good mu. Mu looks like a U, right? So that's the mu. And the rest of these are all lowercase as well. So we're not trying to trick you or anything. They all correspond to the first letter of the prefix name, but you got to watch out for the M's, because there's mega and milli and micro, and they all start with M. Any questions? Well, how do we use those metric prefixes? We're going to talk about how to make conversion factors a little bit later, but I want to go over it now, and I'll go over it again later. So we can make a conversion factor for metric units using these prefixes very easily. Let's say we want to know the relationship between kilometers and meters. Okay, if you're looking for feet and miles, if you don't have that memorized, and the only reason I know it's 5,280 is because I use it every semester, you'd have to go look it up somewhere, right? If I know what the prefix kilo means, I don't have to look anything up. So kilo means 1 times 10 to the third. You memorize it. That's what the kilo stands for. This lowercase k is like an abbreviation for this number. So I put the prefix on one side of the equal sign, and I put what it means on the other side, and then I put the unit that I want on both sides. So if I'm talking about meters, I'll have kilometer and meter over here, and there I have the relationship. 1 kilometer is equal to 1 times 10 to the third meters. And I can do that with any of the units and any of the prefixes. So what if I wanted the relationship between liters and nanoliters? Well, nano equals 1 times 10 to the minus 9. I know that because I've memorized it. Nano and 9 kind of sound alike, so that's how I remember it. So nanoliter is 1 times 10 to the minus 9 liters. So 1 nanoliter is 1 times 10 to the minus 9 liters. Any questions? There are other ways to write these factors that are entirely correct, but in my experience, students mess them up. So let's think about meters and centimeters. Right here I've got a meter stick. This is 1 meter long. Oh, that's not a meter stick. What is a yardstick doing in here? That's just so wrong. Let's pretend it's a meter stick. What to get a meter stick? Good grief. Must be the math people. Anyway, if this was a meter stick, how many centimeters would be on it? 100. So is it true that 1 meter equals 100 centimeters? Yeah, that's true. Does that fit the pattern of what I'm telling you to do? No. The pattern would be put the prefix on one side, centi, and what it means on the other side, 1 times 10 to the minus 2, and then put the meter on both sides. 1 centimeter is 1 times 10 to the minus 2 meters. Is this also true? Yeah, because 1 times 10 to the minus 2 is 1/100th, right? That's equal to 1 over 100 meters. So this is just a different way of stating that. Now, if you are good with metric units and you can use this reliably, that's fine. But in class, I am always going to use this pattern where the prefix goes on one side and the mathematical meaning goes on the other side. The reason is it's really easy to get them mixed up. And I see students all the time tell me that 100 meters is equal to 1 centimeter. That's like saying that 1 foot is 5,280 miles. Is that true? 1 foot, 5,280 miles. That's the distance from here to Minnesota and back. That's not the same as 1 foot. It's easy to get the number on the wrong side of your equation. And so if you follow this pattern, prefix on one side, what it means on the other side, you don't have to understand the relative sizes of the units. You can just follow the pattern and it always works, okay? So I really encourage you to do that. Okay, so what are we measuring? One of the things we measure a lot is mass. Now, mass and weight, we often use those words interchangeably. We'll sometimes say, well, weigh this sample and tell me what the mass is. Well, we're being a little sloppy. Weight is technically a force. It's the force exerted by an object or a sample due to gravity. Gravity is not the same everywhere in the universe. You've probably heard that you weigh 1/6 of your weight on Earth if you went to the moon. Anybody been to the moon and tried that out? That might be fun, huh? Get on the scale and you've lost a whole bunch of weight. Did you lose part of your body when you did that? No. Weight depends on gravity. So obviously, weight is going to vary if you go somewhere else, off the face of the Earth, right? You go out into outer space or you go to a different planet. Nobody's planning to do that during this 4-week session, I'm pretty sure. But did you know that gravity also varies slightly depending on where you are on the planet? It does. Scientists do not use weight to measure how much stuff. We use mass. Mass is a measure of the amount of matter in an object or a sample. It is independent of gravity. And so, although the weight of an object can change, the mass of an object does not change. The gram is the mass unit that we use the most in chemistry, because in the chemistry lab, we're usually dealing with relatively small quantities. We like to do experiments on smaller scales so we don't waste a lot of stuff. It saves on the cost of materials. It also saves on the amount of waste that we're putting into a landfill or a waste disposal site somewhere. So the gram is the most common unit we use in chemistry. It's not the base unit of the SI system. The base unit of the SI system is the kilogram, which we also use sometimes, but it's related to the gram by a factor of 1,000. It's a good idea to have some concept of how big a gram is. we all kind of have an idea of how much a pound is, right? You can imagine, okay, that was a 5-pound sack of flour. We have an idea of how big that is. Gram is a little tougher. So this can help. A US nickel, 5 cents, has a mass of about 5 grams. So a 5-cent nickel is about 5 grams. So the gram is a small unit. We also measure temperature. There are 3 temperature scales that are in common use, Fahrenheit, Celsius, and Kelvin. And the one we use in everyday life is the Fahrenheit. You know, my weather app said it was going to be 80 degrees today. What kind of degrees? Degrees Fahrenheit. They tell you to bake your cupcakes at 350 degrees. It's degrees Fahrenheit because we're silly Americans and we use the English system instead of the metric system. So Fahrenheit is abbreviated degree F. And here's an illustration that shows the relationship between these 3 temperature scales. What we use in chemistry and in science in general is the Celsius scale and the Kelvin scale. And so this shows you the comparison between the 3. So here's the boiling point of water. On the Fahrenheit scale, that's 212. On the Celsius scale, it's 100. So the Fahrenheit scale, there's a little blurb in your textbook about the history of it. Some of these measurements that we have and these units seem kind of random. The fact is that all units were made up, right? There's not really anything such as an intrinsic unit. And we can count things, that's very natural, but any unit was created by somebody. And so there's usually a reason behind why the units mean what they do. So there is a history behind Fahrenheit. I don't expect you to memorize it or anything, but if you're curious, you can read about it. On the Fahrenheit scale, water freezes at 32 degrees Fahrenheit. And 32 is probably a number you're somewhat familiar with. Water boils at 212. So on the Celsius scale, because these are kind of random numbers, aren't they? Or seemingly random. On the Celsius scale, the freezing point of water was assigned a value of 0. And the boiling point of water was assigned a value of 100. It's not coincidence, it was designed that way. And then they divided the difference in temperature between those two into 100 pieces. So the Celsius is truly a metric unit, right? It has to do with factors of 10. Boiling point of water and freezing point of water are very useful because they're very easy to obtain. A lot of our science and measurements and the history of chemistry, a lot of this happened way before the discovery of electricity. They did not have heaters and thermometers and temperature regulation and anything like that. And so how do you get a temperature to make a thermometer for yourself? Well, it turns out that if you have ice and water together, the temperature will be 0 degrees Celsius. If you have boiling water, clean, pure water, it will boil at 100 degrees Celsius. So just about anybody can get those 2 things and they can make and calibrate a thermometer. And so that's why those 2 temperatures are so often used. So 0 and 100. That means that the Fahrenheit degree is not the same size as the Celsius degree. Because between these 2 temperatures, freezing of water and boiling of water, we have 180 Fahrenheit degrees, and we only have 100 Celsius degrees. So the Fahrenheit degree is smaller than yeah, that's backwards. Fabulous. The Celsius degree is larger. You have to switch those. The Celsius degree is larger, right? Because in the same span, there's 100, and here there's 180. Those are smaller. Those are the sorts of things that you don't catch at 1:30 in the morning when you're writing PowerPoint slides. Sorry, I'm in like 3 different group text conversations with my kids. And so my phone is just, I'm going to stick it over here. Hopefully it won't make any noise. It's driving me crazy. And then there's the Kelvin scale. The Kelvin scale was designed to avoid negative temperatures. And the Kelvin scale is very useful when we talk about gases and their properties and behavior. We're not going to talk about gases in this class, but we do go into that in 1A quite a bit. And so we need to be familiar with the Kelvin scale. What the Kelvin scale does is instead of 0 being where water freezes, 0 Kelvin is the lowest possible temperature. It's called absolute 0. It's the lowest theoretically possible temperature. No one has actually achieved 0 Kelvin. They've gotten really, really close. At absolute 0, all movement of particles would stop. Remember I told you how even in a solid, the particles are moving, right? Just like you guys are moving. You're not moving much, you're paying attention, but you are breathing, right? You're breathing. So at 0 Kelvin, at absolute 0, you wouldn't be moving at all. Your heart wouldn't be beating, you wouldn't be breathing, no movement for the equivalent of the solid state in reference to students. So at 0 Kelvin, the individual particles in the solid would not even vibrate. So the relationship between the Kelvin scale and the Celsius scale, the degree Celsius and the Kelvin unit are exactly the same size. They're just offset in terms of where 0 is. So between the boiling point of water and the freezing point of water, there are 100 kelvins. On the Kelvin scale, they're not called degrees. It's just a Kelvin. So there's 100 kelvins, there's 100 Celsius degrees. That means a degree Celsius and a Kelvin are exactly the same size. Any questions? So we need to be able to convert between the different temperature scales. And because of the way they are related, we cannot use just dimensional analysis and convert units like we do with all kinds of other things. We have to use equations. So if we want to convert degrees Celsius to degrees Fahrenheit, oh, good grief. Okay, that's this one down here. I didn't really set this up to be a matching exercise. If we have Celsius and we want to go to Fahrenheit, we're going to use this equation. We're going to take the temperature in Celsius. We have to multiply it by this factor to change the size of the unit, and then we have to add 32 to adjust the 0. And that'll give us the temperature in degrees Fahrenheit. If we have the Fahrenheit temperature and we want the Celsius temperature, then we'll use this equation. We'll take the Fahrenheit temperature, we'll subtract 32 to adjust the 0 point, and then we'll multiply by this factor, 100 degrees Celsius over 180 degrees Fahrenheit. Now, in your textbook, it shows 5/9 and 9/5 instead, because that's the reduced fraction. I prefer the 100 and the 180 because I can remember that. You think about the two temperature scales, and for Celsius, it's between 0 and 100. That difference between boiling and freezing is 100 degrees Celsius. On the Fahrenheit scale, it's 180 degrees, 212 minus 32. So that's why I'm showing you these. So those can be a little tricky. We'll practice them a little bit. And then converting Celsius to Kelvin, you just take the Celsius temperature and you add 273.15, because that's how much it's offset. Now, significant figures when you're doing temperature calculations, some odd things can happen. Let's look at these equations. This 32 degrees, is that, lost the word, Is that an exact number? Is that defined? Yeah, they defined 32 degrees as the freezing point of water. So this is an exact number. The 100 and the 180 are both exact numbers also. And so down here, the 180, the 100, and the 32, they are all exact numbers. So what I want you to do with sig figs and temperatures, instead of going through this equation and keeping track of everything and making your brain hurt, because the units are very similar in size, what we can do is we can just keep the same number of decimal places. So if you start with, say, 25.0 degrees Celsius, and you convert that to Fahrenheit, this had 1 decimal place. Then you report the answer in Fahrenheit with 1 decimal place also. We're not talking same number of significant figures. We're talking about uncertainty in the same decimal place. So let's do an example. Normal human body temperature can range over the course of the day from about 36 degrees Celsius in the early morning to about 37 degrees Celsius in the afternoon. Express these two temperatures and the range that they span using the Kelvin scale. So we're given temperatures in Celsius and we're asked for answers in Kelvin. We need that equation. Okay, so here it is. Kelvin equals Celsius plus 273.15. So Kelvin temperature equals the Celsius temperature plus 273.15. So we have 36 degrees Celsius, right? And we want to convert that to Kelvin. Well, for that one, the Kelvin temperature will equal the Celsius temperature, 36 degrees Celsius, plus 273.15. So 36 plus 273.15. 309.15. What should we do for significant figures? Which digit has the uncertainty in 36? The 6, right? That's the ones place. There was uncertainty in the ones place. So then in our answer here, we want uncertainty in the ones place. The Celsius degree and the Kelvin are exactly the same size. So if we have uncertainty of plus or minus 1 degree Celsius, it makes sense that we should have uncertainty of plus or minus 1 Kelvin. So we would report this as 309 Kelvin. And then it asks us about this other temperature, 37. Well, there, the Kelvin equals 37 degrees Celsius plus 273.15. And that's going to equal 310.15 Kelvin. Where's the uncertain digit in that one? In the what?
In the 7.
Yes. Yeah, in the 37, the uncertain digit is the 7. I was thinking about the answer, and I'm like, I don't see a 7. Sorry. Okay, in the answer, where's the uncertainty then? In the 0. So if we round that, we get 310 Kelvin. If we write it like that, what does it imply, though? According to the rules of significant figures, would that 0 be considered a significant digit? Probably not. At best, we'll say it's ambiguous. If we want to indicate that it's certain, we can put a decimal point there. Looks a little odd. I think the best thing, when you have a 0 like that that could be misinterpreted, put it in scientific notation. So that would be 3.10 times 10 to the 2. Kelvin. That will not be misinterpreted. This 0 is definitely significant. Okay, any questions? What else did it ask us about? The range. What's the range? It's the difference between the high and the low, right? So the range would be the high, 310 Kelvin, minus the low, 309 Kelvin, and that's going to be 1 Kelvin. What's the range in degrees Celsius? Well, the range is the high temperature, so here's the high temperature in Celsius, minus the low temperature in Celsius. So it's still 1, right? So in Celsius, it's 37 degrees Celsius minus 36 degrees Celsius, which equals 1 degree Celsius. Does that bother you? How could it be the same in 2 different units? The size of the units is exactly the same. The difference is where we're measuring from. Where is 0? When you measure a difference, the 0 doesn't matter, right? You're just looking at the difference between one value and another. The 0 part doesn't matter. If you're talking about hiking, right, and you start at 4,000 feet and you hike up to 5,000 feet, you climbed an elevation of 5,000 minus 4,000, 1,000 feet. Well, what if you went from 6,000 to 7,000? You still hiked an elevation of 1,000 feet. How far you are above sea level doesn't affect the distance, right? Any questions? Let's do another one. A body temperature above 39 degrees Celsius constitutes a high fever. Convert this temperature to the Fahrenheit scale. Temperature conversions require an equation. So let's go back and look at the equation. Oops, pressing the wrong button. That never works very well. Okay, so we're given Celsius and we're trying to find Fahrenheit. So we want to use this one right here. So degrees Fahrenheit is degrees Celsius times 180 over 100 plus 32. Always a good idea to write down the equation. So degrees Fahrenheit equals degrees Celsius times plus 32. Degrees Celsius on the bottom, degrees Fahrenheit on the top. It's 180 Fahrenheit to 100 Celsius. There's different ways to remember those equations. You can just flat out memorize them, or you can think them out. I've never flat out memorized them. In a pinch, I think it out, but that takes time. Come back. There it is. So we want to convert 39 degrees Celsius, so we're going to plug it into this equation. So degrees Fahrenheit equals 39 degrees Celsius times 180 Fahrenheit over 100 Celsius. Oh, come on, stop being a slob. Plus 32. In these calculations, you need to be careful when talking to your calculator to make sure that it doesn't misunderstand you. So I'm going to take 39 times 180, and I'm going to divide by 100, and then I'm going to press equals just to be safe, and then I'm going to add 32. and the calculator gives me an answer of 102.2 degrees Fahrenheit. Is that a reasonable temperature for a high fever? Yeah. If we came up with 70 or minus 20 or something, right, we'd go, maybe I did that calculation wrong. Sometimes you can't tell if the answer is reasonable or not, but always ask yourself, is my answer reasonable? What about significant figures? The 39 that we started with, the uncertainty was in the last digit, like it always is, which is in the ones place. And so here, we want the uncertainty to be in the same place, in the ones place. And so we're going to call that 102 degrees Fahrenheit. Any questions? Yeah.
Even though you're like multiplying it, you still do like it's the addition method?
Yeah. There are a couple of small ranges where what I'm telling you to do would not agree with strictly following the significant figure rules. Okay? But I think what's more important than strictly following the sig fig rules is following the spirit, the intent behind the rules, which is to have the uncertainty in the result be comparable to the uncertainty in the starting number. And so that's why I'm telling you, just round it to the same place. It's also much easier. Okay? Yeah?
When you plug it into your calculator, how do you like write it?
Okay, so what I do when I would put this into my calculator is I take 39 times 180 divided by 100. And then some calculators don't understand order of operations very well, and so what I would do then is I would press equals to make sure that it finishes all of this stuff, and then I'll do plus 32 and equals again. So you need to become familiar with your calculator, and that's one of the reasons that I really want you to have your calculator every day, and when I do a calculation, you do the calculation too. That way, if you get a different answer, you know, hey, I've got some problem somewhere, let's figure it out right now. And that's part of why I do these. I write these out because it slows me down. I could make these animations that just pop up and we could get through this much faster. But then you wouldn't have time to punch it on your calculator. So I write it out to force myself to slow down so that you can do it with me. Okay, any other questions? Okay, so there are those base units, but we need some other units as well. Units for volume. There was no volume unit in the base units. That's because the volume units are derived from the unit meter. So if we think about a cube, here's a cube. How do we calculate the volume of a cube or of any rectangular solid? The volume is equal to the length of it times the width of it times the height. You should have encountered that at some point in your career in education. So we have 3 length units that are being multiplied. So if this was in meters, and this was in meters, and this was in meters, we'd end up with a unit of cubic meters. So common units for solid volume are cubic meters or cubic centimeters. Liquids, you don't measure the volume of a liquid by measuring the length, the width, and the height, right? Because liquids they're slippery and they change their shapes, and it's difficult. And so we have to use a container that's calibrated, and we tend to use different units. We use the liter and the milliliter. But these are related to cubic centimeters and cubic meters. So this is a representation of 1 liter. 1 liter is equal to the volume of a cube that's 10 centimeters on a side. So this side is 10 centimeters and 10 centimeters and 10 centimeters. 10 times 10 times 10 is 1,000. So there's 1,000 cubic centimeters in 1 liter. So we look at this picture and we see that 1,000 cubic centimeters is equal to 1 liter. if we take this and we cut it into 10 slices on each side, we end up with 1,000 of these little cubes. Each of these cubes has a volume of 1 cubic centimeter. This volume here is given another name as well. It's called a milliliter. So this whole cube is a liter, and this is a milliliter. The relationship between milliliters and liters can be found using those metric prefixes. 1 milli is 1 times 10 to the minus 3 liters. So this is true, but I would prefer that you do it this way. 1 cubic centimeter is the same as 1 milliliter. This is a relationship that students often forget. Okay, so try to stuff that away in your memory. 1 milliliter, 1 cubic centimeter, 2 different names for exactly the same volume. And then density. Density also uses derived units. Density is a ratio of mass to volume. So it can be expressed with an equation. Density equals the mass of an object divided by its volume. Or we can make that a little shorter, D equals M over V. The original standards for the metric system were based on water. And they set 1 kilogram equal to 1 liter. So they said, well, the mass of 1 liter of water, that's what we're going to call the kilogram. Because of that, then the density of water is 1 kilogram per liter. Because 1 kilogram per 1 liter, because of how it was originally defined. Well, if you change those units to smaller units, you get 1 gram per milliliter. So it's not a coincidence that water has a density of 1 gram per milliliter. It happens because of how the metric system was originally set up. Now we have much fancier definitions for each of the base units. Common density units, grams per milliliter for liquids, grams per cubic centimeter for solids, grams per liter for gases. We use grams per liter for gases because gases are so much less dense that if we use grams per milliliter, we get these really, really tiny numbers. So we use grams per liter and we get more reasonable numbers. So this density equation is one that you should memorize. Density is mass over volume. So here's a graduated cylinder, and they put some water in here, and they put some canola oil in here. And it doesn't matter what order you pour them in. We know from life experience that oil and water don't mix, right? The oil always goes to the top. You could pour the oil in first, and then pour the water in. Doesn't matter. The oil goes to the top because of the density. The oil is less dense than the water. That means if you have equal volumes, and here we do have pretty much equal volumes, the oil will weigh less than the water, even though the volume is the same. You okay with that? Density is something I find a lot of students don't really grasp. The density of something is an intrinsic and intensive property. We talked about intensive and extensive properties. Density is an intensive property, meaning it doesn't change with the size of the sample of matter. Would the volume change if I changed the amount of water, if I took half of it away? Would the volume change? Yeah. Would the mass change? If I took half the water away, the mass would change. Because they both change in the same way, the density doesn't change. Density equals the mass divided by the volume. So I've got, what's it look like there? That's a weird graduated cylinder. Let's just say I have 100 milliliters. So if I have 100 milliliters of water, that's going to weigh 100 grams. And the density is going to be 1 gram per milliliter. If I take that sample of water and I take half of it away, what's the new mass? What's half of 100 grams? 50, right? 50 grams. And if I take half the water away, the volume decreases by half also, right? And I now have 50 milliliters of water. 50 grams over 50 milliliters is still 1 gram per milliliter. The density of a substance is an intensive property, does not depend on how much there is. Just like the color doesn't change. If you have, a tablespoon of water or you have a cup of water, the color is the same. The taste is the same. The density is the same. The volume and the mass change, but the density doesn't change. Any questions? Okay, sample problem about density. Why do ice cubes float in water? Because they're less dense. Something that is less dense will float on something that's more dense. So an iron nail, you throw that in a bucket of water, does it float or sink? It sinks. So is the density of the iron nail greater than water or less?
Greater.
It's greater because it sinks. So we can get an idea about the density of an object by whether it floats or sinks. Okay, so ice cubes float in a glass of water because solid water, ice, is less dense than liquid water. Calculate the density of ice given that at 0 degrees Celsius, a cube that is 2.0 centimeters on each side has a mass of 7.36 grams. Well, that's a word problem, isn't it? When we're dealing with word problems, read through the problem first, and then pick out the numbers. So we've got 0 degrees Celsius, we've got 2.0 centimeters, and we have mass equals 7.36 grams. They want us to find the density. What is density? Mass over volume. So density equals the mass divided by the volume. So that means I need to find the mass of this ice cube and the volume of the ice cube. Did they give me either of those straight up? They gave me the mass. I'm going to go ahead and put that in here. 7.36 grams. Then I need to divide by the volume. They didn't give me the volume. Did they give me information so that I can find the volume? Yeah. Sometimes it helps to draw a picture. So this is an ice cube, a cube of ice, right? So I have an ice cube, and each side is 2.0 centimeters. So that's 2, and that's 2. So the volume is the length times the width times the height, right? 2 times 2 times 2. So the volume equals 2 centimeters, 2.0 centimeters, times 2.0 centimeters, times 2.0 centimeters. This is writing the unit in every time you write down the number, okay? We do the math, 2 times 2 times 2, and what do we get? 8. The calculator will show you 8. How many significant figures should that number have? 2. Because each of the numbers that we're multiplying has 2 significant figures. We do. Well, the calculator's not going to show us zeros at the end. So we need to just put the 0 in. And what's the unit? Centimeters cubed. So there's my volume, and I put that in up here, 8.0 centimeters cubed. And now I can calculate the density. 7.36 divided by 8. Calculator says 0.92. How many significant figures should that answer have? we're going to look at the number of sig figs in both of these original numbers. This one has 3 sig figs, this one has 2. So our answer will have 2. It already does, so we're cool. And then what's the unit? Grams per cubic centimeter. None of those units canceled out, so we just copy them down. Sometimes units will cancel out, sometimes they won't. Any questions? Determine the volume occupied by 23 grams of ice at 0 degrees Celsius. There's 2 different ways to do this problem. We haven't talked about dimensional analysis yet, so we're going to use the density equation. We just calculated the density. So density is equal to 0.92 grams over cubic centimeters. And we know that density is equal to the mass divided by the volume. 23 grams, what is that? Is that a mass or a volume or a density or what? It's a mass. So they didn't say mass of 23 grams, but we should recognize that gram is a mass unit. Gram is a mass unit, meter is a length unit, liter is a volume unit, cubic meters, volume unit, degrees Celsius, temperature unit. So here I have an equation. I want to know the volume down here. I have the mass, I have the density. I can plug those numbers in and solve for volume. This requires a little bit of algebra. I know a lot of you don't like algebra. I'll teach you enough so you can get by, okay? So here I have an equation that I need to rearrange. Up here, this was easy. Density equals mass over volume. We wanted to calculate the density. You just plug the numbers in and you calculate it and you're good. But here, we've got density equals mass over volume, and the thing we want to calculate is down here in the denominator, in the bottom of the fraction. Fractions tend to mess people up. So the first thing we should do, unless you're really good, if you're good with algebra, some of you can look at this and rearrange it in your head. I'm not talking to you right now, you're fine. I'm talking to everybody else. You got a fraction here, let's get rid of the fraction first. And the way we get rid of a fraction is by cross multiplying. Have you heard of cross multiplying? Okay. One of the things that happens when you're out of school for a long time is you remember how to do stuff, but you don't remember the exact words that the math teachers used. You just know how to do it. So sometimes I might say funny things. So to cross multiply, you need a fraction is equal to a fraction. And so let's make that into a fraction. We could divide anything by 1, right? And that doesn't change it. So I've got the density divided by 1 is equal to the mass over the volume. So cross multiplying means I'm going to take the top of one side and multiply it by the bottom of the other side. So I'm going to get density times volume is equal to the bottom of the first side times the top of the other side. What's 1 times m? Just m. So now I have dV equals m. You might be thinking, well, there's no fraction, but we still don't have volume equals something. We're closer though. I got rid of the fraction, okay? So now what I want to do is I want to get the volume by itself, meaning I want to get density to go to the other side. So we look at the relationship between density and volume. They're multiplied. So what I want to do is the opposite of that. So what I'm going to do, this is another step. So I'm going to take this side and divide by density. Why am I doing that? Because density divided by itself is equal to 1. And so those cancel out. It's like magic. Poof! The D goes away. Too bad you can't do that on your report cards, right? Not that you would ever get Ds. Well, if I want this to be equal, I have to do the same thing to both sides of the equals sign, right? It's like a teeter-totter. It was balanced, completely level. If I put a boulder on one side and I don't put an equal boulder on the other side, it's not going to be balanced anymore. So if I divide one side by D, I have to divide the other side by D. So now I'm going to take this messy thing and I'm going to write it without those D's. Now I have volume equals mass divided by density. There's something we can use, right? So now I can plug in the numbers that I've got. I've got a mass of 23 grams, and I have a density of 0.92 grams per cubic centimeters. In the book, and sometimes on the slides too, you'll see units like this with a slash, right? It's so much easier to type that way. You don't have to break out the equation editor and put in a special fraction. So we often type things that way. You don't have a problem with that when you're writing with your hand on paper. So don't write it with the slash. What happens is students don't, it just doesn't jump out at you that you have a fraction there. So don't write it like that. Write it as a vertical fraction like this. Because we have to look at what are the units doing. So first we'll do the numbers. 23 divided by 0.92 equals. And that gives me the number 25. And then I'm going to ask myself, well, what about significant figures? Well, my density had 2 sig figs. And this mass of 23, how many sig figs does that have? 2. It kind of looks like an exact number, doesn't it? But it's measured. It's a mass. It's a measurement. So even though it happens to be a whole number, it's not exact. Also has 2, so my answer should have 2. So 25 is good. Now we got to look at those units. So here we have grams divided by cubic centimeters. We have a fraction within a fraction. And that can be confusing. Well, start by just canceling out the grams. Grams divided by grams. And so down here then I have 1 over cubic centimeters. That's the same as cubic centimeters. And if you want to see exactly how that is, I'd be happy to show you, but not during lecture. Any questions? Mm-hmm.
I always have this problem where I try to break it up the other way by multiplying, but that's not the right way.
So in terms of rearranging this equation, you're multiplying by v.
Yeah.
Well, multiplying by v on both sides would get you this original blue equation here. You just arrive at it in a different way. If you rearrange it correctly, there's more than one way to do it correctly. You'll end up with the same equation. So if you're coming up with the same volume equals mass over density and you're getting it correct every time, then I don't really care what method you use.
I think I stopped right there. I'm not sure what I do, but I took notes, so I'm going to go over.
Yeah, and there will be some other examples where we need to do this. And so if it's not working out, then please continue to ask questions, because rearranging little equations like that is one thing that messes students up. Any other questions?